I'm going to do this afternoon is talk about global wind patterns and currents. So a lot of the pieces that you've been playing with the last 3 meetings, I'll call this morning sort of 2.5 meetings, let's say, we'll start falling into shape. And I just want to give you a little bit of my background. I grew up in LA, and I went to UC Santa Barbara, and I was an aquatic biology major. And so for like our biology, we had divers going out in the mornings and collecting fresh samples from the ocean and bringing it in for our labs. And then I went to Maryland to do my PhD at College Park, and my degree is in marine, environmental, and estuarine sciences. So I worked on the Chesapeake, I worked on the Delaware, I lived underwater for a total of 2 weeks doing research in underwater habitat and coral reefs in St. Croix. But my research was actually on the Amazon, so I spent almost a decade between the Amazon and the Orinoco River in Venezuela working on large wetland systems. So I'm sort of a hybrid between a freshwater ecologist and I also know marine science. And atmospheric science is not my super strong point, but obviously I know some. So if questions come up today during that portion that I can't answer, we've started our parking lot over there. We already have 2 questions related to the tornadoes yesterday, and we'll just add them there and get one of the atmospheric scientists that will be coming in to answer that question. So the ocean and the atmosphere are linked, right? And what happens in one will affect the other. I just wanted to give you a little bit of background information on water, and today what I'm going to try to do is provide some information for later in the week also, especially for the scientist lecture on Thursday, just so you have some of those background information like albedo or whatever. So things may not connect directly with what I'm talking about today, but it'll come up later in the week. So as you recall, here's a water molecule, and we've got our 2 hydrogens and our oxygen. And water molecules have polarity, which means that they have a charge, a slight charge. So at the hydrogen end, we have a slight positive charge, and at the oxygen end, a slight negative. And because of this, this makes water unique, and you get these hydrogen bonds forming. And here's an ice, water molecules in what they would look like in an piece of ice like this here. And as you notice, it's 6 sides. So that's why we get snowflakes that are 6-sided, right? And it's because then the hydrogen can attract the oxygen, and you get this nice lattice work. So water is unique because it has a high heat capacity. And what that means is it can store a lot of energy, or it can release energy. But it does it in steps, right? So we have ice down here. We've got temperature versus heat. So we have ice down here as you start adding more heat, and that's measured as calories. The temperature rises, and then you get to this plateau, and that's called the, if you remember, the latent fusion energy. So what happens along here is there any temperature change? No. No. So you get an increase, you get this little plateau where there's no change in temperature, and then all of a sudden you get to this point and you go up again, and at that point you have water. This is about, this is 80 calories represented here. Has anybody heard sensible heat? That term, sensible heat, does that sound familiar at all? Sensible heat means that as you are putting more energy in, you see a change in temperature. This section is called latent heat. Latent from Latin, latare, hidden. So that's, even though you're still putting energy in, you're not getting any change of energy. So that's called the latent heat. Then we get to the water stage, the liquid stage. Again, we keep putting in energy. The temperature is rising, and then we get to this second plateau. Again, what's this plateau called? Latent. Okay, so we've got the sensible heat, the latent heat. And this takes a lot more energy, doesn't it? So that takes 540 calories per gram to break those strong water bonds, right? So with the ice stage, we've got that nice, the hexagon all bunched together. It's pretty tight. They're not breaking the bonds completely apart. And some may stay together, but some may be loose. So you get a mix with water, and then with the water vapor, once you get up to this point, 2 calories, or kilocalories, then you're releasing all of those hydrogen bonds, and you've got the molecules completely free. And remember, Marcia talked about how water vapor, like steam with your kettle, when you see that water, it's still liquid. But once those molecules, the hydrogen bonds completely break, then they're just floating around. You've got just the individual water molecules, and at that point you can't see them. Does that make sense to everyone? Yes? Okay. And please stop me and ask questions if you need to.
Would this re-describe sensible heat?
Okay, go back. So sensible heat is the portion where you're adding energy and you're seeing a temperature change. So obviously you can be going this way too. What's this? Well, actually, I'm going to show you this slide. So we have, if we're going this way towards ice, we have our gas, right? And we get it condensing, so it cools down, we get liquid forming, then we cool down some more, and we get ice. Then the other way, the ice, you start pouring heat in, warming up, you get liquid, you pour more heat in. It's got to be actually quite a bit more because of that hydrogen bonding, right? So you really need to work hard to get those bonds broken, and then you get the gas. So heat given out, heat taken in. And this is not showing up too well, but we talked about the idea of density and pressure and so forth. So an air parcel moves up, and as it's expanding, it's cooling. So what was an example this morning, or an activity where you were letting the air expand and cool? The balloon. Right. So that was the idea. So as the air rises, it expands and cools. And then as it descends, it's being compressed and it warms up. And again, that's like the balloon when you blow it up, right? Or the tire of the bike. Okay, so now switching to this idea of what Chris Farrell brought up the first lecture, and this is a sentence taken straight out of his lecture. The Earth climate system maintains a balance between solar energy absorbed and infrared blackbody energy radiated to space. The simple way of saying that is that there is the heat is balanced. The heat energy is balanced globally, right? We don't make or create heat. What comes in goes back out on a global basis, right? And here's the his energy budget that he showed you. Lots of things going on, but here we have incoming solar radiation at about 300 watts per meter squared. And I didn't print this out, but we'll have this available on the thumb drive. And then we have the reflected and the outgoing long wave, and they both equal this number, okay? So globally, the energy balance is, or the energy budget is balanced.
Just to clarify there,
Yes.
but you keep saying the global energy is balanced, so in one spot it's not necessary.
I'm getting to that.
Oh, okay, I'm just clarifying, okay.
Can I ask a quick
Yeah.
question? So the energy that comes in and the energy that leaves is the same, but yet we have bodies on the planet that are absorbing energy. So how can it be the same going out?
Well, it's, there's lots of, it can be reflected, it can be absorbed, it can be, this back radiation. So just globally balanced, globally it all balances out. And I would say you have to take the scientist's word. Plus it's, just a simple fact of physics, matter's not created or destroyed, energy not created, so we have to go by what theory is. But that's a good question. So first I'm going to talk about large-scale wind patterns, and then what plays into that is this whole idea of there is uneven heating on the Earth, which you just saw when you were doing that flashlight activity, right? And Chris also talked about it. So within a given band on the globe, the energy balance is not, or the energy balance isn't balanced, or the energy budget, excuse me. So as you saw with your flashlights, when you shine directly at the equator, you can see there's a lot more energy hitting than at the higher up latitudes, and then if you're way up here, you're going to have a huge angle, and then part of the year you have total darkness, and part of the year you have complete daylight. So because of this unevenness, this drives atmospheric circulation. Okay, here's that convection current that we were talking about. There was lots of discussion. I love listening to all of you when we were doing the smoke box activity about if the air was getting sucked or pulled or whatever. So basically that was a convection current. So what happens is you've got your little heater here along the wall. It heats up, the air rises, and then it gets up here, it's cooler, becomes more dense, and it sinks, and it moves back this way. So you start getting this nice convection current within the classroom. That's what we saw with the smoke box, with the smoke. So given this concept, this would be the theoretical global wind patterns if we had an Earth that was all water, no land. And it wasn't spinning. Okay, so just a beach ball that's sitting there. So what would happen is these along the equator, that's where we're getting most of our heat energy, and we get the air rising. It moves northward, it starts cooling, sinks down, and comes around. So you would get just these big, huge cells in the two halves of the Earth. But that's not, life is not quite this simple, of course. We have something called the Coriolis Effect, right? So, and I know you guys all told Marcia, so which way is the Earth spinning? West to east. So here's our little spinning here, and we got the North Pole. And so if you're standing at point A, because the Earth is spinning, it's going to look like if you dropped, let's say we were at the top and we were able to like roll a marble down, it would swing out this way and eventually make a clockwise circulation. And the reason why, so these 2 points are at the same, let me see, what would that be? Longitude, latitude. The same points. But you can see at this point, in order to make it around in 24 hours, it's going to have to spin faster, right? Because it's got a longer ways to go. This point here has a shorter way to go around this disk. So just the differential between the speed of the planet makes things look like it's spinning or being deflected. And in the southern hemisphere, things look like they're spinning counterclockwise. So clockwise in the northern, counterclockwise in the southern. Think of some big ocean event, phenomenon that happens, that swirls. Hurricane, right? So in the northern hemisphere, hurricanes spin counterclockwise. You do? Oh, you're right. Sorry. Never mind. But when water goes down the sink, it goes clockwise up here and counterclockwise in the same hemisphere, which is interesting. Okay. So then the other thing, we have the Earth spinning, but we also have land masses in the way. Okay. So and this is. This is taken from Chris. So here is the total amount of energy hitting. So obviously you're getting more between this 30 degrees. And then we actually have a deficit within the polar regions here. So between having the land masses and the Coriolis effect, what we have then are several different cells that turn atmospherically. Okay, so here we have the warm air rising, and you could imagine that it's going to be wet, right? Because at the equator, we have a lot of evaporations. It's warm there, so the water's evaporating, and as it rises, it brings that moist air up into the air here, and then as it cools, it starts raining. What we all know in the tropics, right? We get high amounts of rain. When I was doing my work in the Amazon, it rained 2 meters per year, so 6 feet of water. We get 18 inches here. So the water goes up, the air goes up, cools down, you get rain, and then it drops down at about 30 degrees, and then you get this circulation. This circulation, and I'll go this way, it's easier for me to reach down here. In the southern hemisphere, we're going the other way, and what happens is you get this air with the friction starting to move the opposite way. So you get these different cells, this one's going this way, this one's going this way, another 30 degrees, and then we have the polar region where there's a polar cell, but it's not as obvious of a circulation pattern as these two. Yes?
So I understand the idea of it raining in the tropics. So what happens on the other side of the globe, like in Africa, where that?
Well, I was just going to get to that.
Okay.
So we've got, so here we've got the known as the equatorial lows or the doldrums. So right where the air is starting to move, you don't have a lot of motion this way. You have the motion going up, and I'm going to show a pretty dramatic slide of that. Then these areas where you have descending air, what do you think the air is as far as humidity? How much air do you think, or how much water do you think is being held in that air compared to what's going up? Very little, okay, because it gets rained out essentially, right? So along these areas where you have descending air, that's where we tend to have our desert zones. So in Africa, like in North Africa, where it's so dry, that's along that 30-degree latitude where the air is descending and there's just not much water in the air. What do we have here? We have desert in the southwest, right? And then these cells actually have a name. So the first set of cells between 0 and 30 are called Hadley cells. Not that you need to know that, but if you ever hear it, you'll know what that is. And then further north, between 30 and 60, is the feral cells. And again, you get the clouds forming up here because it's sweeping the water up. And then at the very top, you have the polar cells.
So Leslie, this whole thing is, this diagram indicates that the cells, the Hadley, the feral, and polars are pretty much due strictly to the sun-hidden eclipse.
Mm-hmm.
And so the feral cell is sort of like a backwash, as the air from the Hadley cell is descending.
Exactly.
It's just drowning
Yeah,
in there.
it's like, and you get the same thing
Kinda like
going
an
on in
egg or
water.
whatever.
They're called Langmuir cells. If you ever look out in the ocean when it's windy, you get these things setting up to the perpendicular, and you'll see lines, and it's because there's these big cells setting up in the ocean, and where one's going up, it pulls the next one down, and typically you get lots of productivity there because things get trapped in between there, and you get nutrients and phytoplankton and fish and all sorts of interesting things. So boundaries are very interesting places. What happens in atmospheric boundaries? Obviously, we don't have nutrients and phytoplankton and fish, but what often happens along boundaries? Storms, right? So, let's see. I think the next slide is shows a little bit simpler. So I just wanted to show you something a little bit simpler without all the cells. So then, remember we've got the Coriolis Effect. So in the north, it's moving. So you got these big cells going vertically, but you also have going this way. So, you know, it's a 3D structure, right? The atmosphere as well as the oceans. So it's sort of a lot to think about. So you've got these little mini wind patterns setting up, right? So we are located, let's see, we are in the, we're not in the trade winds. So we have the westerlies are what affect us, right? Because our wind, which direction does it usually come from? West to east. Down in South America, it is the other way. So it's the other direction. And then we have in between these pretty predictable winds. I mean, it's pretty often that we have, if it's windy, it's going from the west to the east. You get the doldrums along the equator and the horse latitudes. And the sailors, you know, way back when that's how people got around, not, you know, back in the 1500s, 1600s, they took advantage of these winds, right? And sometimes you would read about how they would get stuck in the horse latitudes and just sit there, and then, you know, maybe a current would pick them up. But they took advantage of the winds as well as the currents to get from Europe over to North America and so forth. Okay, everyone clear and set? I just wanted to mention this one story. So here's a picture of the Western Hemisphere, and I was working about right here on the Amazon and where the Rio Negro comes. So, you know, the winds are just this really nice, coming from the east, sort of helps cool things down. We were doing research on a floodplain lake, and we lived in the middle of the lake. We had what we call a flutuwanchi, which means floating house. So big, huge tree trunks that are buoyant, and then we had a series of those with our house built on it, and we lived there, and we had our lab and so forth. And it was just anchored on one anchor, so it would pretty much was always, you know, set up where the wind was coming this way, and our flutuwanchi would be this way. So, you know, we were the gringos there, and everyone else were locals. There was no electricity. You could only get there by boat. You know, it was quite remote. And one day, the wind shifted dramatically, and it started coming from the Andes. And, you know, we had no idea what was in store, but all the locals were going, oh no, this is going to be a storm of the decade. And I'm like, what does that mean, you know? So they all knew, you know, because they'd lived it all their lives there and probably had stories about storms like this. Well, it started raining and raining and raining, and our boat, which we had a little metal boat to get around, we had to keep running out and, you know, bailing it out so it wouldn't sink. And at night, our anchor actually started dragging, and I thought, great, we're gonna just go right out into the Amazon and we'll be down at the Nels, you know? And that year it ended up raining just a huge amount, and the river actually breached all the levees, so it was just like all one big sheet of water. So they really knew, you know, what it meant when the storm was coming from the other way, that it was just going to be a huge whopper. It was really interesting. The other thing is, sometimes the winds would get very strong and come from the south rather than from the east. And this would happen oftentimes when it was fairly cloudy in December. It was sort of the winter time. And when that would happen, it was really interesting because the lake was very deep at this time of the year. It was 30 feet, and it was what we call stratified. So on the top part, it was really warm, and then the bottom part was cooler, and they wouldn't ever mix. And the bottom part would go anaerobic, so there was no oxygen in the bottom. So again, the wind shifts, and all the locals are going, oh no. And we're like, what does that mean? And sure enough, the next day, we had to do temperature and oxygen readings every morning at 6 a.m. when we woke up. We would do it every meter, just to see what the lake profile looked like. And I got out there, and I'm like, there were fish going like this on the surface. I thought, oh gosh, I bet it's anaerobic all the way. And what had happened was, because it had been cool, and the surface had started cooling enough, and it doesn't mean very much in the tropics, the bottom and the top sort of flip-flopped and mixed. And so the whole thing became anaerobic, and all the fish were up at the surface gulping because they needed oxygen to breathe. And the locals loved it because they got out there with their fish nets and they just started fishing like crazy, and they were grabbing their fish. So it's sort of a different perspective about, you know, the weather patterns and local knowledge and what that means to this, you know, the local people there. It's pretty interesting. Okay, so that's sort of the stage for the big scale wind patterns. But we also have small scale wind patterns that more affect us that we like yesterday. So cold air is dry, it's dense, and it creates zones of high pressure. Warm air is the opposite. It tends to be moist, as we saw, like at the equator. You get the evaporation, you get the water evaporating into the air. It's actually less dense because the water molecules displace the air molecules, and it creates zones of low pressure. So the question is, which direction will two air masses flow if they meet? And that's sort of, again, like we were talking about with the smoke boxes. So I've got a couple different examples. This first one is called a sea or lake breeze. If you have a large lake, you can also get this phenomenon happening. So, you know, morning comes, the sun is shining evenly. Because water has that high heat capacity, it takes a lot of energy to get the temperature to change, it doesn't heat up quickly. Whereas the land has a much lower heat capacity. So it can warm up much quicker, and what happens? You get the warm air rising, and as my Latin teacher used to say, nature hates a vacuum. That's the way I always think of it. If you get the warm air rising, this cold air will rush in to fill that vacuum. And you mentioned that, a partial vacuum. So during the day, what we get is called an onshore breeze, right? So it's going from the ocean or from a large lake to the land. and you get this convection cells setting up essentially. Now, at nighttime, we get a land breeze. So the sun goes away, again because of the lower heat capacity, the land can cool faster than the water. Then the water becomes more warm relatively. It's not like it's heating up, but relatively it's not going to cool as fast as the land. So then you start getting the air warming up, expanding and rising. And again, you get that cold air filling in that vacuum, and you get the flow going the other way. So we have a land breeze. The wind is going from the land out to sea. Does that make sense? Now, we have the mountains. Oftentimes we'll get in the evening mountain breezes going on. So where does it get cold first? The mountains. Higher up, right? So the air here starts cooling, and we actually get draining because that air is denser than the warm air. So it drains down into the valleys and forces that warm air up. It's not quite the same idea as the vacuum, but it's sort of, in this case, it's pushing it down. And you get this type of flow going on. And then we get the Chinooks, and I'm not going to talk a lot about the Chinooks, but we all know about them. We're going to have a speaker later in the week talk about, or maybe tomorrow afternoon. The scientist from NOAA is going to sort of talk about local weather phenomena. And Linda, I don't know if you know what a Chinook is.
It's a strong wind, is all I remember.
Yeah, because they don't happen really in the summer. It's a winter phenomenon. You come in the summer, don't you?
We felt them and seen them in summer.
Yeah. So he's going to be talking about it, and we're also going to ask him these questions about the tornado. I think he'll answer that. Okay, so again, here's just another nice graphic. This is the equator where you get the most amount of heating, you get evaporation, the warm air rises, it's got a lot of water in it, you get the raining out, the air becomes dry, less dense, falls at that 30-degree latitude, just one second, and you get those desert bands, very intense in northern Africa. Yes?
So this woman that I work with says that science never sucks, which means there's never a sucking motion of air or anything, except that you were just saying that there's a partial vacuum.
Well, it's not really a vacuum, but I mean, that's how I sort of conceptually think of it. It's like, okay, the water, it's
So is it-
rising up, so something is,
So is it pushing in or sucking? Because that's a big
That's what I was.
misconception.
oh,
I mean, it's a
okay,
big-
yes.
There's a big preconceived notion that it's sucking the cold air just the same way like an egg is sucked down into a jar, so just
Well,
really
and I-
pushing.
No.
I mean, so
Yeah.
I'm just curious, what's the correct scientific
No, I mean,
theory?
sucking would not be the correct term, and that's just the way, I'm sorry. That's just the way I conceptualize it, yes.
Technically, it would be, as Bernoulli's principle states, a low pressure system.
Yeah,
Which is lower, so it's that
Right.
the sun has to
It's
supplant that.
pushed.
It's pushed in, right?
Pushed
It's not
down
sucked
because
in.
it wants to move from a higher concentration. to a
Right.
lower concentration.
and so you can sort of think of it also in terms of diffusion, where you go from a high pressure to low pressure. Does that make more sense?
Yeah, no, it makes sense.
Yeah.
I just didn't know. I'm just saying there was. a
You know what,
person
and
that-
again, that might be a good, Marshall, would you mind writing that down on the board, because that might be a good question on the parking lot.
So what was the question exactly? Is it
Just
Sucking or.
pushing
Is
or,
there a
pushing or,
vacuum or is it to push a high pressure system to low pressure, which is pushing the air?
and I can't tell you for certain,
Okay.
so we'll find that out to make sure. That's a good question. Yes.
So this here, too, this diagram you have up here, you know, you always hear the weathermen talk about low pressure in the higher latitudes and middle latitudes and surface lows. So this is what's causing different pressures at different altitudes.
Mhm. Well, and then also, so that's again this vertical, but we've got this thing going on too, right? So that's
Well,
when it gets
again,
more
you know,
complicated.
the weather, particularly in the winter time, I always talk, especially when we get deep snows, they talk about low pressure at the surface.
We'll
And then
be,
they'll say low pressure in the
Yes.
upper atmosphere,
right,
but it has to do with.
it's
what
layered
columns
for
that are
sure,
moving.
yeah. And we're gonna be doing an activity on the computer with, the big snowstorm in 2003. So,
Oh, cool.
let's see. The one thing, my husband works for NOAA, he's an atmospheric scientist, and when I showed him the slide last night, he said, these are extremely intense, and I know that because I lived along the equator, storms, and this is where that plane went down, was in, this is called the ITCZ, the Intertropical Convergence Zone. And he said what the theory is, the Airbuses have been having problems with these little tubes that they use to bring air in to figure out, so they know what the airspeed is. And so you've got a lot of water, and when it's really intense and it rises up quickly, it can freeze. And so these little tubes have been having problems freezing over, and they think maybe what happened was that the tubes froze and the plane had no idea what airspeed it was going, and the autopilot shut down. So these are pretty intense, you know, and I guess there must not have been an indication that there was this big, huge storm where they were flying into.
Well, and they can go up to 50,000 feet, so
Yeah, very
you can't
high.
fly over them, and they're so huge, it's hard to
Yeah,
fly around them
Yeah.
sometimes.
and here's just a nice picture. You know, when I lived in Brazil, I would often see, I mean, the cumulonimbus clouds are just incredible there, you know, and we had such a nice view, and we'd be sitting there in our little Flutuanchi with the tin roof, and you'd see just this wall coming, and it's like, oh gosh, get inside, you know, and then it rained so hard and for so long that, you know, you'd have to get right next to each other and just shout as loud as you could to be able to hear each other. It was intense. Okay, so now I'm going to talk about, we're going to switch to currents in the ocean. And currents are created by wind, the surface currents, okay? So you get the wind blowing along, and there's friction, and you get this water piling up, and then on the other side there's less pressure, and it moves along. And not surprisingly, because of that Coriolis effect and the wind patterns, we get the same patterns for the currents, the surface currents, right? So we get a clockwise rotation up in the northern hemisphere, and counterclockwise in the southern hemisphere. And what we get are these large gyres. So they're just big, huge circular movements between the continents. So in the north, so here's North America, here's California. So we get the North Pacific gyre, we have the South Pacific gyre, we have the North Atlantic gyre, and the South Atlantic gyre, and then the Indian Ocean. Too much landmass here, we obviously don't have ocean there. So we've got these 5 huge gyre systems, and as you notice, we have red and blue. So obviously the water in the equatorial region is much warmer, gets circling down, picks up the cold water gets warmed up. So you get this nice circulation pattern. And in the middle of these gyres, it's often very low productivity. Not many nutrients, not a lot of phytoplankton, not a lot of fish. So those are sort of known as deserts in the middle of the gyres. And then we have up in the pole regions, we have along the Antarctic circumpolar current, which obviously just sort of goes around along the Antarctica. So if we were looking at the North Atlantic gyre and I said something about western boundary currents, where is the western boundary current in the North Atlantic Gyre? If you're looking at the whole picture there.
East coast of the US.
It's the east coast of the US. So it's, you don't want to think of, well, this is the east coast, so this is the eastern boundary. You have to think of this big picture here, that whole region. So along the western boundaries, that's where we have the really deep, very well-defined boundaries, or currents. And what color are they? They're red, okay? So they're bringing water up from the equatorial regions and around. Here we get a little bit sneaking off up towards Northern Europe here. And along here we've got, along the southern part of South America. So these bring the warm water from the equatorial regions to the poles. So that's helping to move heat from the equator out to the poles and bring warmth.
Can I ask, why are the fastest and deepest currents found?
Let's see. It has to do with the Coriolis Effect. And I can't tell you like the specific physics of it, but again, the Coriolis affects both this and this.
I have another question.
Yeah.
Okay, so you've got the surface flows.
Yeah, and they reach down to about 400 meters.
Okay, because it seems as if the water, I'm sure if the water goes northward in the pools, that water's going to sink, right?
Well, I'm looking at this now. So the Gulf Stream is a really good example of a western boundary current. How many people have been to the East Coast and been in the ocean? So almost everyone. Paul has it. Let's see what it's like. How many people have been to the West Coast and been in the ocean there? Big difference, right? So here is the Gulf Stream. So it's coming up from the equator. It almost looks like a river, doesn't it? I mean, this is it right there. So it's very well defined. It comes up from the equator. This is Cape Hatteras, North Carolina, and it tends to veer off and then head to the east. The interesting thing about the Gulf Stream is, you notice this feature here, and this here, and then there's another ring here. So the red is the warm water, and then as you get more towards the blue is the cold water, okay? So you get these, this is a warm water ring. You can notice how it's sort of a circle. And this is actually a cold water ring in the middle. So you get these interesting rings that spin off, the warm waters spin off, the cold waters get entrapped and then they spin off. And you get some really interesting biology going on. And they stay very distinct for a long ways off, and they head off to Europe, and they can stay in a ring like that for hundreds and hundreds of miles. So it's pretty interesting. I thought I read this in a book. It can move 160 kilometers per day, and its flow is 300 times the Amazon River. And the Amazon River has the highest discharge of any river in the world. It actually supplies 10% of the world's oceans, the fresh water for the world's oceans. And that's 300 times that flow. So it really cooks. So you can imagine the ships, back when we were colonies, would take advantage of this and move along to get over to Europe faster.
That would also kind of explain why when you see hurricanes going down, it seems it takes forever to go from there to Florida,
Mm-hmm.
but then they just zip off.
Yeah, and that could be. Maybe it's just moving along. So, and then of course the winds also are going favorably in that direction too. So, if those old ships could pick up the Gulf Stream and then you got the westerlies, you could get over Europe pretty quickly, I bet. Okay, so the eastern boundaries, and again, this is because of the Coriolis effect, they are much more slow-moving and diffuse, so you don't get that real distinctive band that you can pick up in the radar. And then what they do is they move the cold water towards the equator. So they take the water, they move the water from the poles down towards the equator, and then it'll get warmed up again and continue this pattern. So when you go to California and you go swimming in the summer, everyone thinks, oh, it's going to be really warm. The water is freezing. You go to the East Coast in the summer where it's so hot and humid. And I went to graduate school in Maryland, and we'd go down to Ocean City, and oh yeah, the beach, it's going to feel so good. And you get in there, it's like, oh, this is like a bathtub. So it's interesting. People that don't live on the coast may not even realize that there's a difference between the Pacific and the Atlantic in temperatures. Probably a lot of your kids don't. I love this quote. The coldest winter I ever spent was a summer in San Francisco by Mark Twain. So the surface currents and ocean temperatures affect our local weather and climate. And I'm not going to say a whole lot about this. I have a question about this because this is something that we're going to be looking at temperature data and so forth, and you're going to be pondering over. But when you do this activity, think back on your what you learned about the currents and which way they're moving and from the north and the south and so forth. Okay? Okay, so now I'm going to start talking about sort of this more the deeper currents and what you brought up. Remember when I talked about doing the temperature profiles when I was working in Brazil? Oceanographers often, when they do their work, they're looking at temperature and oxygen profiles. So this is a typical profile where we have temperature from 0 up to 24 and depth. And in the surface, obviously it's warmer. Why? Sun, right? So the sun is hitting the surface and it warms it up. And we call this the mixed layer because you get sort of a mixing at that top layer. You get a rapid decrease in temperature, and that's called the thermocline. And then it's pretty steady temperature and quite cold at the bottom. In the surface, oftentimes the nutrients are very low. Now, why would that be? No, there's more oxygen. Well, until you get to the deep. What's using the nutrients?
All the other animals.
Not animals, plants. The phytoplankton. So they're sucking up the nutrients, okay? And so the nutrient levels are lower than in the deep part. Then what happens is, so you've got your phytoplanktons and so forth up on the surface. They're producing oxygen, right, because they're photosynthesizing. So you get high oxygen. Oftentimes you'll get oxygen dropping. You may get fish feeding on them and so forth. These things die and they sink down into the sediments, and then they get decomposed and so forth, and then the nutrients get released. And because of this thermocline, it really acts as a pretty good barrier between the deep water and the mixed layer. So you don't get a whole lot of mixing from the deep to the surface. So the nutrients tend to be trapped down in the lower portion of the water column. So you get cold water, you get higher nutrients, warm water, less nutrients. I've also got this funny word called a pycnocline. Does anybody know what that is? It's not salinity, but it's related. It's the density. So you would have a very similar pattern if you were measuring density. So again, thermocline, you get this rapid change in temperature. The pick the kind, you get a rapid change in the density of the water. So the less dense water is on top. That makes sense, right? Warm, less dense. Top, bottom, more dense, cold. Okay. Okay. So we get coastal upwelling areas, and which is shown in the red. And when we get upwelling from the deep ocean, all of a sudden you're bringing up a lot of those nutrients. So these red areas tend to be the very productive parts of the ocean. Because remember I said in the surface layer, usually it's pretty low in nutrients because the phytoplankton have been using up all the nutrients. So in this area where you get upwelling, you get the really nutrient-rich water coming up to the surface, and then all of a sudden you get intense productivity going on. You get lots of phytoplankton, you get fish feeding, and so forth. This is where the Peru and the anchovies that you hear about, and El Nino and La Nina, which I'm not going to talk about because, again, that's going to be lectured later. But the El Nino and the La Nina have an effect on this upwelling and on the fisheries. And Jeff will be talking about them on Thursday. So that's another type of current that's very important globally.
So should I wait to ask the question?
But
Wait till Thursday, what the cause for the upwelling, since it's high density cold water, what the hell is that?
yeah,
Yeah, so
Thursday,
yeah.
like I said, this is sort of the introductory cursory part for Thursday's lecture. So that there, besides the surface currents, there's this very deep water mixing that's going on in the oceans too, and that's called thermohaline circulation. And so remember at the surface, what I said were those currents are driven by wind, right? The wind blowing across and the friction. The thermohaline circulation is created by density differences of water. So thermi being heat, halos being salt. Thermohaline. In terms of how important this type of circulation is, it's very important. It circulates about 90% of the world's waters on a very long time scale, which I'll tell you about in a minute. But so the surface is only responsible for about 10%. So if you're thinking about moving warm water from the equator to the polar regions and balancing the how much heat there is in the equatorial regions and getting some of that cold water down, which type of circulation is more important in the oceans? It's this deep water, very slow mixing. And as I say, the whole ocean is involved with this. This is a really busy slide. I'm just trying to show that there are different masses of water. So the combination of temperature and salinity are very important in water, and that affects its density. Yeah. So here we have the Antarctic. I'm going to talk a little in a minute about the Antarctic bottom water, but each color indicates a different type of water mass within the whole global ocean. And oceanographers measure temperature and density. You can just measure temperature and density and you'll know what mass of water you're sitting in. And it's big, huge areas of water masses. And this slide just shows, can you see this is really light and that's dark? So water masses, just like in those boundaries with the air, they don't mix well. And you get these turbulent areas, and like I said, they're very important areas of productivity because you get nutrients trapped there, and the phytoplankton get there, and then the fish are attracted. So these boundaries are very important biologically. So this one you can see the difference. It's obviously this has got more sediments in it, so that's why it's this color. But you can most likely go for a long ways before this water will mix. It'll stay, you can go along the boundary and it'll stay black and it will stay brown and it won't mix, just a little teeny bit along the edges, but it will stay two very distinctive bodies of water. So the Antarctic bottom water is really what starts this whole thermohaline circulation. So it forms just along the margins of the Antarctic. And what happens is it really starts to freeze quickly. The ice excludes, well, let's see, the water freezes, the salts are excluded from the ice, right? Because ice is fresh. So the water's cold and it's getting more saline because the ice is getting ejected. It's very saline, it's very cold, it's -5 degrees. It's the most dense water mass of all the water masses. So you get this water forming and then it slowly sinks to the bottom and spreads throughout the ocean basins. And it takes 1,000 years for it to resurface. So that's a very different time scale than the surface current.
How do they know?
You know, I would imagine, I don't know for certain, but scientists use tracers, and they could inject a tracer in there and follow it, and obviously they can't do it for 1,000 years, but you know, they know where the water goes because they can take water samples at very deep depths and track where it goes, and then probably just by extrapolation, you know, it's going this far in this amount of time, you know, to get all the way around, it's going to take, that's what I'm assuming. We can ask Jeff that.
They could probably inject it in different areas along the
Yeah.
way too.
Mhm. Yeah. So I would imagine, and like I'm saying, I'm just taking a guess, but I would think it would be some sort of tracer that they're using. So what we get then with this circulation is you get the deep water forming, it sinks, it goes down, it goes back up. Oh, no, I'm sorry, I'm looking at the blue. The blue is the cold water, it sinks at this point and then it comes up. This is not a very good, it's not looped very well. But you can see how it's involving all of the basins, and it's bringing the cold water down, and then the warm water surfaces. The water surfaces, gets warmed up, and then goes back to the poles. I've got this little nifty graphic, which I'm not really good at doing this sort of thing, and I don't know how this is going to show up, Jim, but is it okay if I escape it? If it doesn't work here, I'll give it to you guys in the computer lab. It's this nice 3D graphic that I found. Next one. Oh, and the interesting, so for every liter of water that sinks, 1 liter has to come back up. So again, there's this nice equilibrium balance, right? You can't have a bunch of water sink and nothing happen in response, right? So you just think of that heavy, cold water just slowly but surely, you know, and as it's sinking, then something else is rising. Let's see if I can get this Well, I'm going to give this to you in the computer lab because it's a really neat 3D graphic where it shows it sinking and it's coming up by a continent, and then it shows a slice this way as well as from the top. It's from Jet Propulsion Lab. So. Okay, so what are the take-home messages today? I like this question. Let's see, can I keep it like that, Jim, or is that going to be? Okay. So the interesting question is, if the equator is receiving excess energy and the poles are getting a deficit, why isn't the water boiling at the poles and frozen solid never to melt at the equator? And why is it not freezing solid and never melting at the poles? And it's because of the winds and the water, right? Both are working together to move the warmth of the equator to the cold polar regions. So the currents and the winds are carrying that excess energy from the equator and taking it up to the poles, and then the cold air is coming down to the equator to help cool the equator too, so we don't get the equator boiling either. The atmosphere transfers about 2/3 of the total heat. The ocean's only about 1/3. If I were just sort of thinking about it myself, I would think the oceans would be more important, but it's actually the atmosphere is more important. And then the last thing is, what would happen if the patterns of the winds and the currents change? And this is the question about climate change. If we change these patterns, what is going to be the effect of us here? Is it going to get drier? Are we going to have droughts? What's going to happen in the poles? Are we going to lose the polar bears in the tropics? Are we going to start seeing more coral dying and so forth? These are questions that scientists are working on right now. And as Chris and Ula talked about with the ice sheets and how that's changing with time too. So that's that, and I was just